In 2013, Elon Musk introduced a bold idea: a transportation system faster than trains, cheaper than high-speed rail, and nearly as fast as an aircraft. He called it Hyperloop. The concept was simple, yet revolutionary. What if we could travel between cities at the speed of sound, all without ever leaving the ground? It sounded like something straight out of science fiction. But Musk released a detailed white paper laying out the engineering principles behind it. He made the concept open source, inviting engineers and innovators around the world to take the idea and run with it. The world took notice. But what exactly is Hyperloop, and how is it supposed to work? Is it the future of transportation, or an impossible dream? At its core, Hyperloop is a proposed high-speed transportation system for passengers and cargo. Imagine a long sealed tube connecting to distant cities. Inside this tube, a passenger pod or capsule is propelled at incredible speeds. The entire concept is built on overcoming the two biggest enemies of speed: air resistance and friction. Think about when you stick your hand out of a moving car window. You can feel the air pushing back against it. That's air resistance, or drag. The faster you go, the stronger that push becomes, and it takes a massive amount of energy to overcome it. The other enemy is friction. For a typical train, this is the friction between the wheels and the track. Hyperloop aims to conquer both of these physical limits. The goal is to create a mode of transport that is not only faster, but also more energy efficient and cheaper to operate than existing high-speed options. It's a fundamental rethinking of how we move from point A to point B. So, how does Hyperloop tackle air resistance? The secret lies in the tube itself. The system is designed to remove most of the air from the tube, creating a near-vacuum environment. We're talking about reducing the air pressure to about 1/1000th of the normal atmospheric pressure at sea level. Why is this so important? Because with almost no air inside the tube, there's almost nothing for the pod to push against. The drag becomes incredibly low. This is the same principle that allows objects to move freely in the vacuum of space without slowing down. By creating this low-pressure environment, a Hyperloop pod can achieve extremely high speeds using surprisingly little energy. It's like turning a 100-kilometer sprint into a casual jog. The pod doesn't have to fight the air. It can just glide through the near-empty space. This is the single biggest innovation of the Hyperloop concept, setting it apart from every other form of ground transportation. Now, with air resistance out of the way, what about friction? Traditional trains have wheels that roll on steel tracks, creating rolling friction that consumes energy and limits speed. Hyperloop gets rid of wheels entirely. Instead, the pods are designed to levitate, floating just above the track. There are a couple of ways to achieve this. The primary method is magnetic levitation, or maglev. This uses powerful magnets on the pod and the track that repel each other, lifting the pod into the air. With no physical contact, there's no rolling friction. Another proposed method is using air bearings. This involves pumping a thin layer of compressed air underneath the pod, creating a cushion of air for it to float on, similar to an air hockey table. Once the pod is levitating, how does it move forward? This is where linear electric motors come in. Instead of a rotary motor that spins wheels, a linear motor is laid out flat along the track. It uses changing magnetic fields to propel the pod forward smoothly and powerfully, without any moving parts on the pod itself. This combination of levitation and linear propulsion is what allows for a frictionless, high-speed journey. So, just how fast are we talking? The theoretical top speed for a Hyperloop system is over 1,000 kilometers per hour. That's around 700 miles per hour. Let's put that into perspective. The fastest high-speed trains in the world today top out at around 350 to 400 kilometers per hour. Hyperloop is designed to be more than twice as fast. A commercial airliner flies at a cruising speed of about 900 kilometers per hour. This means Hyperloop could offer airplane-like speeds, but on the ground, imagine traveling from Los Angeles to San Francisco in just 35 minutes, instead of a 6-hour drive or a 1-hour flight, plus all the time spent at the airport. It would completely change the way we think about distance and commuting. You could live in one city and work in another, hundreds of kilometers away, with a daily commute of less than an hour. This level of performance is what makes the Hyperloop concept so compelling. One of the most ambitious parts of the original Hyperloop proposal was its energy plan. Musk envisioned the system being not just energy efficient, but a net energy producer by covering the top of the entire tube with solar panels. The idea was that the vast surface area of the tubes, stretching for hundreds of kilometers, could collect a significant amount of solar energy. In theory, the solar panels would generate more than enough electricity to power the entire system, the vacuum pumps, the linear motors, the station operations with surplus energy to spare. This excess power could then be stored in battery packs or even sold back to the grid. This would make Hyperloop a self-sustaining, carbon-neutral mode of transport. Of course, this is the ideal scenario. Real-world challenges like weather, nighttime operation, and the efficiency of energy storage make this a very difficult goal to achieve. But the vision of a transportation network that powers itself is a powerful one. For all its revolutionary potential, Hyperloop faces enormous safety and engineering hurdles. These challenges are the main reason we don't have a commercial system up and running yet. First, there's the tube itself. Building and maintaining a perfect vacuum seal across hundreds of kilometers of steel tube is an unprecedented engineering feat. Even a tiny leak could compromise the entire system. Then there's thermal expansion. The steel tube would expand and contract with temperature changes, which requires complex expansion joints to prevent buckling. Safety is another huge concern. What happens if a pod gets stuck or loses power inside the tube? How do you safely evacuate passengers from a sealed vacuum tube? And what about natural disasters? The entire structure would need to be resilient to earthquakes, which is a major issue in places like California, where Hyperloop was first proposed. Finally, there's the staggering cost. The infrastructure for Hyperloop would be incredibly expensive to build, with some estimates running into the tens of billions of dollars for a single route. These are not small problems, and they require brilliant and expensive solutions. Despite the challenges, the idea of Hyperloop captured the imagination of engineers and investors worldwide. Following Musk's 2013 paper, several companies emerged to try and turn the concept into a reality. The most well-known was probably Virgin Hyperloop, which built a test track in Nevada. In 2020, they conducted the first-ever human passenger test, reaching a speed of about 170 kilometers per hour. It was a major milestone, but still a long way from the promised speeds. Another key player is Hyperloop Transportation Technologies, or Hyperloop TT, which has been developing its own technology and proposing projects around the world. There have also been numerous university competitions sponsored by SpaceX, where student teams build and test their own pod designs. However, the initial hype has cooled down significantly. Virgin Hyperloop shifted its focus away from passenger transport to cargo, and eventually laid off much of its staff and closed its test track. As of today, no commercial Hyperloop system has been built, and the path forward remains uncertain. The dream is still alive, but it's proven to be much harder to realize than first imagined. So, with all these setbacks, is Hyperloop a failed experiment? Is it destined to be just a footnote in transportation history? Maybe not. Even if a full-scale Hyperloop system is never built, the project has already had a massive impact. It forced the transportation industry to think outside the box. It pushed the boundaries of what was considered possible in engineering. The research and development that went into Hyperloop has advanced key technologies. It has spurred innovation in magnetic levitation systems, which are being explored for other applications. It has driven progress in vacuum engineering and material science. And it has highlighted the immense potential of creating more energy-efficient modes of transport. The legacy of Hyperloop might not be the tube itself, but the ideas it inspired. It serves as a powerful reminder that progress often starts with a question that seems impossible to answer. What if we could do things completely differently? In the end, Hyperloop is not science fiction. It is a bold engineering proposal colliding with the harsh limits of real-world physics, economics, and logistics. It's a grand vision that aimed to redefine speed and efficiency. Whether it eventually becomes our daily commute or remains a fascinating case study in ambitious engineering, Hyperloop has proven one thing very clearly. Innovation doesn't start with small, safe steps. It begins with bold ideas that dare to challenge the status quo. The journey to the future of transportation is a long one, and Hyperloop, successful or not, will be remembered as a significant leap along that path. Thanks for watching, and subscribe to the channel for more deep dives into the technology that shapes our world. See you next time.